Today we are going to see the Vizing theorem. Before that, we will see some results. Let G be a connected graph that is not an odd cycle. G has two edge coloring in which both colors are represented at each vertex of degree at least 2. Proof of the result. Let us assume that G be a non-trivial connected graph. That is, G has more than one vertex. Exactly one vertex. G has exactly one vertex. It is called a trivial graph. Here G be a non-trivial connected graph. Therefore, G has more than at least two vertex. Suppose G is Eulerian. Eulerian graph means G is Eulerian graph means G contains a Eulerian tour. That is, Eulerian tour means that is we have an Eulerian tour, Eulerian trial which traverses every edge of G. If G is an even cycle, then we have a proper two-edge coloring of G in which both the colors are represented at each vertex of degree 2. So G is an even cycle, then alternatively we will give the colors 1 and 2, then we get proper two-edge coloring of G in which both the colors are represented at each vertex of degree 2. Suppose if G is not an even cycle, then G has a vertex V0 of degree at least 4. Since G is Eulerian, therefore every vertex of G has even degree. Let V1, G is Eulerian, therefore Euler tour exists. Let V0, E1, V1, E2 be script C, V0 be an Euler tour of G. Define E1 equal to the edge EI, I is odd, and E2, EI, I is even. That is, edge set in the Euler tour can be partitioned into E1 and E2. Then, two edge coloring E1, E2 of G has required coloring. That is, we give the edges in E1 by the color 1 and edges in E2 by the color 2. Then we have two-edge coloring E1, E2 of G has required coloring. Therefore, each vertex of G is an internal vertex of this Euler tour. Suppose G is non-Eulerian. Non-Eulerian means G contains odd degree vertices. We construct a new graph G star by introducing a new vertex V0 and joining it to each vertex of odd degree in G. Consider the graph G. Here these two vertices are odd degree. Now introducing this vertex and connecting to the odd degree vertices, these two vertices, we got G star. Now the every vertex in G star is even degree. Therefore this is an Eulerian graph. Therefore this is an Euler tour of, that is, we move from this, that this is an Euler tour of G star. Define E1 equal to EI, I is odd. E2 equal to EI, I is even. Then two edge coloring E1, the edges in E1 intersection with the edges of G and E2 intersection with the edges of E of G. That is, this is the required property. That is the E1, the edges colored by the color 1 with intersection with the edges of E and the edges colored with color 2 intersection with edges of G, we give two edge color. Therefore, then two edge coloring of E1 intersection E and E2 intersection E of G is exist. This is the required property. Given a k-edge coloring script C of G, let us denote the number of distinct color represented at vertex V of G by script C of G. Script C of V1 equal to 1 and script C of V2 equal to 2, script C of V3 equal to 2 and script C of V4 equal to 1. Here we see the vertex in vertex V1, the color 1 represented at V1. That is, for this edge 1 and for this edge 1, that is only one color is represented at V1. Therefore, script C of V1 equal to 1. Here the color 1 represented at V2, color 2 is represented at V2, that is 2 colors are represented at V2, therefore script C of V2 equal to 2. Consider this vertex, here the color 1 is represented at V3 and 2 is represented at V3, therefore the 2 colors are represented at V3, therefore script C of V3 is 2. In consider V4, here the color 2 is represented at V4 and the color 2 is represented at V4, that is only one color is represented at V4, therefore the script C of V4 equal to 1. Suppose script C is a proper k-edge coloring, then degree of V equal to, that is number of colors represented at V. That is, here we give proper k-edge coloring, that is for this edge G, that is green, white, red, and this is red and green. Here green, white, red, yellow, and G, here G and R. So adjacent edges have distinct colors, that is this graph have proper 4-edge coloring. Here degree of V1 is 3 edges, that is these 3 edges. These 3 edges, that is degree of V1 equal to incident at V1, therefore degree of V1 is 3, and the number of colors represented at V1 is 3, therefore degree of V1 equal to number of colors represented at V1 equal to 3. Consider V2, that is degree of V2, the number of edges incident at V2 is 2 and the number of colors represented at V2 is also 2, therefore D of V2, D is script C of V2 equal to 2. And consider this vertex V3, here number 1, 2, 3, 4 edges are incident at V3, therefore degree of V3 is 4 and number of colors represented at V3 is 4, therefore degree of V3 equal to number of colors represented at V3. Consider this V4, that is here 2 edges are incident at V4, degree of V4 is 2 and 2 colors are represented at V4, therefore the script C of V4 is 2, therefore they are equal. Here D5, here only one color is represented yellow, that is degree of also one edge is incident at V5, the degree of V5 is 1 and number of colors represented at V5 also 1. Therefore, if proper k-edge coloring exists, then degree of V is always equal to the number of colors represented at that vertex. A k-edge coloring script C dash of C dash is an improvement of k-edge coloring script C if the sum of the colors represented at every vertex is under the edge coloring C dash is always greater than the number of colors represented at each vertex under the k-edge coloring C is always greater than. Here consider this example. Here sum of the script C of V equal to, that is in 1 we have only one color represented 1 and V2, that is 4 colors are represented G, Y, R, Y, that is 3 colors are represented. Here this edge also Y, this edge also have Y color coloring with Y, therefore 3 colors are represented at V2, therefore it is 3. And V3 with the 2 edges are having different colors, therefore V3 number of colors represented at V3 is 2, the number of colors represented at V4 is 3 and the number of colors represented at V5 is 2, therefore total sum is 11. Now the same graph can be recolored, that is recoloring. Here the difference is this edge has yellow color, here we have the white color, that also, that is in V2 we have the in this graph we have the proper edge coloring, that is R, Y, G, here also distinct colors and all the edges have distinct colors, here also distinct colors, that is in V1 only one color represented and V2 that is 4 colors are represented, V3 2 colors are represented, in V4 3 colors are represented, in V5 2 colors are represented, that is 5 5 plus 5, 12, that is that recoloring C dash of V equal to 12. That is in C of V, sum of C of V equal to 11. Here C dash of sum of C dash of V is 12. Therefore C dash is the improvement of C. Optimal KH coloring. An optimal KH coloring is one which cannot be improved further. That is proper coloring always cannot be improved further. That is optimal KH coloring is one which cannot be improved further. Here consider this example. This is an optimal KH coloring. That is we need 4 colors to color this graph, and it is also a proper coloring. It is also an optimal KH coloring. So we cannot give more than 4 colors for this graph. Next result, lemma, let script C, E1, E2, etc. Ek be optimal KH coloring of G if there is a vertex VI in G and color I and J such that I is not represented at U and J is represented twice at U. Then the component heights of graph induced by the vertices of EI union EJ that contains U is an odd cycle. Let U be the vertex that satisfies the hypothesis. What is hypothesis? That is, there is a vertex VI in G and colors I and J such that I is not represented at U and J is represented twice at U. That is, U be the vertex. Here the I is not represented at U and J is represented twice at U. That is the component the graph induced by the edges G of EI union EJ is denoted by height which contain U. Suppose height is not an odd cycle. Height is not an odd cycle by known theorem. Height has 2 edge coloring in which both colors are represented at each vertex of degree at least 2 in height. Here, this result we have already seen. When we recolor the edges of height with color I and J in this way, we obtain new KH coloring. That is, here we have U be the vertex such that I is not represented at U and J is represented twice at U. If we recolor, I is represented at U and J is also represented at U. That is, a new KH coloring is script C dash, that is E1 dash, E2 dash, EK dash. This is the new KH coloring. Here, script C dash of V denote the number of distinct colors at V in C dash. If C dash of U is, that is in first script C of U equal to in C of U, that is one color is not represented, but in new coloring I is represented and also J is also represented. I is not represented, J is represented twice at U, but in new coloring, that is J is only once colored and color I is used. Therefore, C dash of U equal to C of U plus 1. Both I and J are represented at U. In all the vertices, other than U, all the vertices C dash of V always greater than or equal to C dash of V for C of V for V not equal to U. Therefore, considering these two, this sum always greater than, that is, this is greater than C of C dash of U is always greater than C of U. Therefore, we get the summation C dash of V is greater than summation C of V, which is a contradiction to the choice of C. Since we have chosen the choice is optimal KH coloring, therefore it cannot be improved further. Therefore, which is a contradiction. Therefore, height is indeed an odd cycle. If G is any simple graph, then I dash is greater than or equal to delta. Del is the maximum degree of the graph. That is, maximum degree of the graph means any vertex having the degree del, which is the maximum degree of the graph. Therefore, there exists a vertex V such that D of V equal to del. That is, maximum degree of the vertex is V. So, there are del edges incident at the vertex V. That is, all the edges are incident, that all the del edges are adjacent. Del edges are adjacent means it is a proper coloring, then it has distinct colors. So, we required at least del colors to proper coloring of the edges of G. That is, high dash is the minimum colors used in the proper coloring. The number of minimum colors used to color in the proper coloring. So we required at least del colors to be proper coloring of the edges of G. Therefore, high dash of G always greater than or equal to maximum degree of the graph. Here if G is bipartite, then high dash equal to del. It is enough to prove that is we know that every graph high dash is greater than or equal to del. That is here we say that high dash greater than or equal to del. In bipartite we have to prove that high dash equal to del. That is in bipartite we have proved that high dash are not greater than del. Suppose by the contrary, suppose G is bipartite graph with high dash greater than del. That is, let script C be the del edge color, optimal del edge coloring of G. That is, we have used del number of colors. Since high dash is the minimum number of colors to color the edges of the proper coloring. That is high dash, now we have assumed that high dash greater than delta. High dash greater than delta means this is not a proper coloring because we have used del colors to color the graph G. Therefore, this coloring C is not a proper coloring. Let U be the vertex such that C of U less than D of U. That is not proper coloring means any vertex receive the same color for adjacent vertices. Therefore, in U it may be one color is not represented and some color is represented more than once. That is C of U less than D of U. Now consider del edge coloring at U. Some color I is not used and J represented twice. By lemma, that is I is not represented, J is represented twice, then G contains an odd cycle height. We know that G contains an odd cycle, but which is a contradiction. Since we consider here bipartite graph, we know that bipartite graph has no odd cycle, so which is a contradiction. We know that for any simple graph, high dash greater than or equal to delta, therefore high dash always equal to del. Vizing theorem, if G is simple, then either high dash equal to del or high dash equal to del plus 1. Let G be a simple graph. By the previous theorem, G is bipartite, then high dash equal to del. We need only to solve that the high dash less than or equal to del plus 1. Suppose we have to prove that high dash less than or equal to del plus 1. Suppose high dash greater than del plus 1. We assume that high dash, that is chromatic number, edge chromatic number is always greater than del plus 1. Let script C equal to del plus 1, E1, E2, etc. E del plus 1, the optimal del plus 1 edge coloring of G. That is, we have used the colors of C by number of colors is del plus 1 and U be the vertex such that C of U less than D of U. Since this is an optimal del edge coloring, also side is greater than del plus 1, therefore N is at least one vertex will must receive the same number of colors for its edges represented at U. Therefore, the coloring is an optimal del edge coloring of U. U be the vertex such that C of U less than D of U. Then there exists I0 and I1 such that I0 represented at U but I1 represented at least twice at U. From this figure at U, that is I1 represented twice at U but I0 is not represented at U. Here let U V1 have color I1 as shown in figure A. That is U V1 color represented by I1. Since D of V1 less than del plus 1. Since the degree of the vertex V1 is less than del plus 1, some color, because this is the maximum degree of the graph, plus 1, that is any vertex in G, the degree of that vertex is less than del plus 1. Some color I2 is not represented at V1. That is, we used del plus 1 colors. Therefore, certainly the I2 or any color is missing at V1. Any one of the color is missing at V1. that is represented at I2. Now I2 must represented at U, since otherwise by recoloring U V1 with I2 we would obtain improvement on C. Now we consider I2 must be represented at U, then recoloring U V1 with I2 we would obtain improvement on C. Thus some H V2 U has color I2. Since it is an improvement on C2, but we consider C is the optimal del plus 1 edge coloring, therefore it is not possible. Thus some edge V2U has color I2. Again D of V2 less than del plus 1, some color I3 is not represented at V2 and I3 must represented at U. Since otherwise by recoloring U V1 with I2, U V2 with I3, we would obtain improved del plus 1 edge coloring, which is not possible. Proceeding like this, some edge U V3 has color I3. Continuing this procedure, we construct a sequence V1, V2, etc. of vertices I1, I2 of colors such that U Vj has color Ij. Ij plus 1 is not represented at Vj. Since D of U is finite, there exists a smallest integer L such that for some k less than L, then Ik equal to I L plus 1. Because it is D of U is finite, the number of edges incident at U is finite, therefore there exists smallest integer L such that for some k less than L. Therefore Ik equal to I L plus 1. Now recolor G as follows, that is 1 to k minus 1, the colors V12, that is k minus up to k minus 1, U Vj with the color I J plus 1, yielding a new del plus 1 edge coloring script C dash, E1 dash, E2 dash, E del plus 1 of G. Now we have, that is U V1 colored with I1, U V2 colored with I2, U V3 colored with, that is U Vj colored with Ij, therefore that is colored with V2 figure, it is V1, it is V2, it is V3 and it is V3, it is V2, it is V1. Clearly C dash of V greater than C of V for every V belongs to V, and script C dash is also an optimal L plus 1 edge coloring of G. The component H dash of G of E Ik dash union I naught dash that contains U is an odd cycle. Now in addition, U Vj with color I J plus 1 from the vertex k less than or equal to j less than or equal to L minus 1 and U V1 with the color Ik to obtain del plus 1 edge coloring C double dash, E1 dash, E2 dash, E double dash as the following figure in C. That is, here U V1 I1, U V2 I2, Ik plus 1, that is Ik, and this is Ik plus 1. Up to here we have I naught, that is in Vk minus 1 Ik and I naught are represented, that is we consider the Ik double dash and I naught double dash that contains U is an odd cycle, that is 1, 2, 3, 4 and 5, that is H double dash is an odd cycle with the component, this component contains H double dash, this is denoted by H double dash, this contains a U is an odd cycle. But since Vk has a degree 2 in H dash, since Vk has a degree 2 in H dash, clearly Vk has a degree 1 in H double dash, that is here Vk has a degree 2 and here Vk has a degree 1, Vk has a degree 2 in H dash and Vk has a degree 1 in H double dash, but H double dash is an odd cycle containing U, therefore which is a contradiction. This proves that our assumption is wrong, therefore high dash greater than or equal to del and high dash less than or equal to del plus 1, high dash equal to del or and high dash equal to del plus 1. That's all.